Okay, so I told some of my discrete math students that I would make a video for them because we didn't finish covering this one in class. So this is that. So the question, just for anyone else who might be viewing, is the following. So we define a relation on the positive integers. These should be positive integers. On pairs of positive integers, I should say, where a, b is related to c, d, if and only if a plus 2b is equal to c plus 2d. Okay? So the first part of this question wants us to determine if this is an equivalence relation. So I'm going to leave all of that stuff to you. Of course, if you really ask me nicely in the comments, maybe you're stuck on this, perhaps I will make a follow-up video on how to deal with all of that, how to prove that formally. But there were some questions from tutorial about how to provide a rigorous proof of the rest of the problem, which involves asking questions about the number of elements in an equivalence class. So in particular, two questions essentially that exist are, are there any equivalence classes with 13 elements, and I think the other one is 273 elements. So what we're going to talk about is how to provide a rigorous proof. We're going to solve a much more general thing because 273 elements, that's a really tough one to go check by hand. So we're going to try and prove a sort of general formula for the number of elements in an equivalence class for this relation. So first, in order to get some intuition, the stated hint for the exercise was to say draw a picture and come up with a geometric interpretation of this equivalence relation. So that's what we're going to do. So I'm going to plot the integer points, the positive integer points. So this is the 0.11, this is the 0.12, and so on and so forth. So give me a second to draw here. You should be writing everything out as I'm going anyways, to follow along. So it's also an opportunity for you to draw this little grid. And this keeps going. And the idea is that, well, maybe if we draw this out, we draw some of the equivalence classes out, it'll give us some insight into how to solve this problem. So let's start with the most basic one. Let's think about the equivalence class of 1, 1. Well, the equivalence class of 1, 1 is what? It's going to be the set of all pairs C and D such that 1, 1 is related to C, D. But what is that? This is going to be the pairs of all C, D, where, so it's 1 plus 2 times 1, which is 3, is equal to C plus 2D. So let's try and find all of the pairs that do that. Well, we know automatically that 1, 1 is in the equivalence class, right? It has to be. So we ask ourselves, what are the possible solutions to this? And we want to make sure that C and D are integers, of course, right? So how could we possibly solve this equation? So let's think about this. So D has to be a positive integer. So that means the smallest that D could possibly be is 1, right? So if D is 1, this second term will be 2. And can we choose an integer C that will make this equal to 3? Yes, that's 1. But of course, that's just the 0.11. We already know that belongs to the equivalence class. What else could possibly be in there? Well, we have 3 equal to, now again, we're thinking about, so this was case 1. This was when D was equal to 1. That was the smallest possible choice. So the next choice is, what if D is equal to 2? Well, if we tried that though, 2 times D is going to be 4. And the problem is, yes, there is an integer I could choose for C that would make this equation work out. But the problem is we need both C and D to be positive integers, right? So if we look the way that this problem is stated, we're specifically only considering positive integers. And the only C that would work in this equation is -1. That's not positive. So that's it, right? And then we can see that if we pick any D that's bigger than that, we're going to run into the same problem, right? This term here is just going to be too big. So in fact, the equivalence class of 1, 1 is just a singleton. So 1, 1 is the only element that's related to itself. Okay. So then what about the equivalence class? You know, we go to the next one and we ask, well, what about the equivalence class of 1, 2? Well, same thing. So, and I'm going to jump ahead a little bit. So we start off, you know, I would recommend, especially if you're doing this on the quiz or the exam or something, you know, write out the whole thing carefully is to make sure to not trip yourself up. Write out each step. But I'm going to jump ahead and write this out. This ends up being, we want the set of all pairs C and D so that C plus 2D is equal to 5. So again, the smallest that D could be is 1. So let's see, we would have 5. We would need 5 equal to C plus 2. So we see that, yeah, I could take C to be equal to 3 in this case, and that would work. So the pair 3, 1, which is here, is in that same equivalence class. Awesome. What else could I possibly take D to be? Well, I could take D to be 2, potentially. Then I would get 5 plus C plus 2 times D is 4. And so we see, oh yeah, C, we have a positive integer solution. But that's just the pair 1, 2 itself. Again, we expected that to be in the equivalence class. And then finally, again, for D greater than or equal to 3, we see that this term here is going to be at least 6, and now this term is bigger than 5. We run into that same problem. C would have to be negative, and so therefore these are all the elements of the equivalence class. And so if we keep going in this manner, we actually see what the pattern is they all seem to sit on parallel lines. Now, hopefully you drew this out on some graph paper, you know, maybe with a ruler or something, so that it's a little clearer for yourself. But okay, give me a moment here to just draw some lines. And the point is, if you draw out all of these equivalence classes, you can see that these points are yeah, like I said, just exactly the ones that are on these sets of parallel lines. So give me a moment here. This will have 2 here as well. And let me draw out one more. Maybe I'll leave this one in blue. So that goes through here, and that goes through here. There's another point here that I didn't draw in, and so on and so forth, right? So you can see as you keep doing this, it's all going to be these parallel lines. So how does this help us? Well, we know that lines, you know, if you think back to like high school mathematics, we know that every straight line is of the form y equals mx plus b, right? We have an equation of this line. And so basically, we know that the equivalence class of some point is just going to be the set of points on the line where x and y are both integers, right? Positive integers in particular. So this will help us solve the problem. Now let's try and think about what that might be, right? So if we write this out a little more generally, the equivalence class of a pair A and B Again, this is going to be the set of all coordinates. Now, maybe I'll call it x and y. You'll see y, pun intended, in a moment. So it's going to be the set of all pairs in z plus cross z plus, such that AB is related to xy. So again, we haven't even come close to starting sort of the formal proof or argument yet, but we will shortly. So just hang on. We're still in exploration mode. So I'll write just the same thing here, and this is the equation, right? I'm just writing things out again very carefully. X plus 2y. So now we can see actually how to manipulate this equation, though, right? So basically, this just becomes the set of all points where if I rearrange this equation, so I'm going to do a couple steps at once into y equals mx plus b form, this becomes y equals to negative x over 2 plus a plus 2b over 2, right? So in terms of our y equals mx plus b form, this is like our m is minus 1 over half, and well, I don't really want to write b because we're already using b for something else, but we can see, to put it in other terms, the slope would be minus 1/2, and the y-intercept would be this term, right? Okay, so in other words, in other words, the equivalence class is going to be the set of all pairs x and y, such that, what is it? It has to be on this line. So we have this equation that has to be satisfied, right? And but there's a couple other things. There's a few other things that I forgot to write here. I mean, they're implicit in the fact that these have to be positive integers, but let me try and turn those into formulas over on this side. So we could imagine that this is now a point in R2, and I'm going to turn the restriction to positive integers to some formulas here, because you'll see in a moment that that's actually going to help us count things. So where we want, of course, x and y to be integers, and we want both x and y to be greater than 0, right? So if I rearrange this formula a little bit, so I'm going to arrange it again so that we have the formula is 2y is equal to minus x plus a plus 2b. We can see that this condition actually forces this term to be even, right? Because that means that this is 2 times some integer. And conversely, if this term on the right was 2 times some integer, well, we would just take y to be that corresponding term, right? So we can rewrite this set yet again to be the set of all xy, such that, and now this just becomes the condition that a plus 2b minus x is even. And we want x to be greater than 0. But the condition that y is greater than 0, we can rewrite this as well, right? So if I want y to be greater than 0, well, that would be the same thing as saying that 0, so just replacing y with this formula here, that would be the same thing as demanding that 0 is less than minus 2x plus a plus 2b over 2. Multiplying the whole equation through by 2, we get that 0 is less than, and I just want to put the minus signs over to the right, just a personal preference, how I like to write things, would be this equation. And then maybe adding things to both sides, we get that x has to be less than or equal to a plus 2b, right? So this becomes, now we can turn the condition on y being greater than or equal to 0, we combine this into just one string of inequalities here. Okay, fantastic. Now what we're going to do is break into separate cases. So one of the clues that we might want to break into separate cases here is the fact that we're dealing with when a number is even or not. So that's a clue. Whenever you have a parity consideration, maybe you want to break into two separate cases. Now, strictly speaking, you don't always have to break into two separate cases just because you see the word even and odd, right? So you have to stop and think about it. But in this case, definitely our restriction on x here, it's going to matter whether or not a or b is odd or even. So that's what's determining really in this case that we want to break into separate cases. So let's do that. So case one. Suppose that, and so now here maybe is where things aren't quite so formal yet, but we're almost there. So suppose that a is even, right? Well, what does that mean? Hence, we can choose we can choose an integer L in the integers such that A is equal to 2 times L, right? And so now, if we think about it, hopefully we're thinking about it this entire time. If A is even, right, so we have 2L plus 2B minus x, and we're demanding that this entire term is even, well, that will only be even if x itself is even, right? This whole term here, if x were odd, this whole term would be odd, right? So this entirely depends on x, right? So now this whole even condition simply in the case of A being odd, now becomes a condition simply on X being even, right? So I can rewrite the set above again, and in fact, I'm gonna rewrite the Y over here entirely in terms of X. So this will be 2K. 2K. How do I rewrite this in terms of this will be 2K, and then Y is 2L. Right, that's A plus 2B minus negative x over 2, so that would just become minus k in this case. And now the even condition has entirely been absorbed into making, so here I'm thinking of x as being equal to 2k. So the even condition has been entirely absorbed into this. So finally, to rewrite this one last time, actually, there's a couple more things I want to do here. So let me rewrite the L. Let me rewrite this as L. Yeah. So to do one last rewrite on this set, everything in this inequality here is even. So I can divide through by 2, and again, I get k between 0 and L plus B. And now, in fact, what is this? Well, k, remember, this has to be a positive integer. So it's going to be, it can't be anything in between 0 and 1. So the smallest it can actually be is 1. And it's definitely going to be allowed to be 1. And the largest it can be is L plus B minus 1, right? So finally, we get that this will be equal to 2k for 2L plus 2B over 2 minus k, such that k is between 1 and L plus B minus 1. Now, you might be thinking, okay, I've been at this for like 10 minutes, 15 minutes, 20 minutes. What is the advantage of writing it like this? It seems like the set is so much more complicated than the set we started with. Well, notice the advantage here is that now this depends entirely on one parameter, right? We're just counting the integers between 1 and L plus B minus 1. And how many such integers are there? Well, there's just L plus B minus 1, right? That's exactly the number of integers between 1 and L plus B minus 1, right? So this actually gives us a formula, right? In other words, I'm making the claim that if if A is even, right? And recall that then we are writing A as 2L, which is to say that L would be A over 2. So if A is even, then the cardinality of the equivalence class of A and B is A over 2, so that's what L is, plus B minus 1, or to write this slightly differently, adding some of my fractions together, this would be A plus 2B over 2 minus 1. Or if you preferred, you could also absorb that 1 into there, so A plus 2B minus 2 over 2, for example. So that's my claim. Okay. So certainly we can argue that, if you follow the typical recipe for counting elements of a set, if we knew that the equivalence class was equal to this, then we could just perform that recipe to explain the counting here, right? You could just say something like, well, since, right, you could say the set on the right, there's one element for each k between minus 1 and L plus B minus 1 inclusive, this gives the result. So now that we have our guess for this formula, let's talk a bit about how we would prove this more formally. So let's talk about the proof of the claim. Proof of the claim for the even case, right? So suppose A is even. I know I already said this above. And choose L in Z such that A is equal to 2 times L, right? And let's think about what our goal is, right? So I want to prove that these sets are equal. So I'm going to move over here a second. So I'm trying to prove that A plus B is equal to the set of all pairs 2K, and let me go and see what I wrote here, 2L plus B minus K, was it? Minus K, where K is between 1 and L plus B minus 1, right? So I'm trying to prove that these two sets are equal. How do I prove that two sets are equal? Well, I need to prove two statements. I need to prove first, for all x in for every element of the set on the left, that element belongs to the set on the right. So maybe I'll just be lazy and define this to be S. And conversely, for all y in S, I need to convince you that y belongs to this element here. Okay, so let's go ahead and do that. So let's begin with the first one, right? So let, and I don't know, maybe I'll call it CD. Let CD be an element of the equivalence class of A and B, right? So by definition, C plus 2D is equal to A plus 2B. And, probably we're going to have to make use of the fact that A is even. So I'm going to right away include in here that this is 2L plus 2B, right? Just by the replacement above. Now, what are we trying to show, right? We're trying to show that the pair CD belongs to this set here, right? So what do I need to do in order to do that? Well, I need to convince you of two things. I need to convince you that C is equal to an integer of the form is equal to 2 times some integer k, where that k happens to be between these two values. And I need to convince you that D is equal to 2L plus B over 2 minus K, right? So there's basically 3 goals on my checklist. So let's go ahead and prove that, right? So the first thing to do is let's isolate C to try and get the first thing on our list, right? So thus, C is equal to 2L plus 2B minus 2D. And hey, I wanted to show that C was 2 times some integer. Things are lining up pretty nicely for that. So I just need to factor out a 2, and we get L plus B minus D. And then we could say since L plus B minus D. And we could even do something sneaky here, because we know that we want to work with this this integer k, right? So to get it in this exact form, let's make a definition. Let's get 2 birds stoned at once and define k to be this integer. So I'm doing 2 things in this one line. I'm defining k to be this integer, and I'm reminding the reader that L plus B minus D is in fact an integer, so that I can say C is even. Well, not such a big deal. I mean, what we really just want is C to be equal to 2 times some integer, right? So great. So that's the first thing on our checklist. Great. So we've got that done. And again, keep in mind, this checklist I'm writing here on the right, this is my rough work. This is not the good copy that's being handed in on my final exam, let's say. Now let's look at this other term here. So I want to prove that this term I've come up with satisfies these bounds, right? So again, we're gonna let's do a little, making a little box here for us to do some rough work in. So I want to show that k is between these two things. Probably I should show them both separately, right? So let's focus on k being greater than or equal to 1. Well, what was k equal to? That was L plus B minus D, right? So this is L plus B minus D, right? Okay, time for a sip of water. But remember, so we have to think about, we might want to, so I'm going to do 2 things at once. I'm going to look at, well, where did this come from, right? It came from C plus 2D being equal to A plus 2B. So how could we sort of combine these things? Well, C plus 2D, try and make these 2 things look more similar to each other. C plus 2D, that was 2L plus B, right? Okay, that's looking pretty close. That's looking pretty close to this. How do we make things even closer? Well, maybe I could move this D over here. So I have C plus D less than or equal to L plus B. Okay, how do we make these things look closer? Oh, sorry, there should be a 2B here. Well, there's a 2 missing, right? So maybe if I multiplied both sides of this equation through by 2, I could get 2 plus 2D less than or equal to 2L plus 2B. Aha, so we're very, very close. The only other part of the puzzle that we would need to know is that C would have to be at least 2. right? C would have to be at least 2. But we know that C is equal to 2k, and we've also assumed that C is a positive integer, right? So if it's a positive integer, it was positive, and it's even, the smallest positive even integer is 2. Great. Okay, so now we need to go back and try and assemble these things into a large, into a coherent argument, right? So let's go through these steps, and the step that we want to start with is here, right? Because this is our starting assumption, and we want to work through all of this logic to basically arrive at this, or rather, I should say, this inequality, right? So we could say something like, well, by assumption, C plus 2D is equal to A plus 2B. And what could we say? Well, and as C is a positive even integer, C is at least 2. Thus, 2 plus 2D is less than or equal to C plus 2D, which is equal to A plus 2B. And remember, we wanted to somehow get our L involved here, right? We're trying to go from this equality, going down through our various steps in logic and trying to work back up to here. So let's do something to get that L involved. Of course, we know that A is equal to 2 times L. So that's what I'm going to do at this step in the argument. So 2 times L plus 2B. Okay, great. So what I'm going to do is take a second to now combine these and really focus on what's important here, right? The very left part of the inequality and the very right part of the inequality. So I might say something like, therefore, 2 plus 2D is equal to 2L plus 2B. And this implies, dividing by 2, that 1 plus D, there should be less than or equal to. 2 plus 2D is less than or equal to 2L. Keep making little typos. L plus B. And finally, this implies that 1 is less than or equal to L plus B minus D, and that was equal to K. Nice. Okay. So we have accomplished the second thing on our checklist, right? Well, half of the second thing on our checklist. I wanted to convince you that K is at least 1, right? So I would also recommend, for clarity, because there's a lot of steps going on here, I didn't quite do this here super clearly, but for each one of these parts of the verification, I would maybe start a new paragraph to make it clear where each thought is, and maybe even highlight along the way what it is we're proving in each of these steps. So what's the next thing we need to show as part of this series of inequalities? Well, we want K to be less than or equal to L plus B minus 1. Right, so we want K to be less than or equal to L plus B minus 1. But again, K we define to be L plus B minus D, less than or equal to L plus B minus 1, right? And, well, how could we... So again, we'll try and work almost backwards to something that we know is definitely true. If we knocked out the L plus B from either side, we would get minus D is less than or equal to 1. Multiplying both sides by minus 1, we get D is greater than or equal to 1. And this is something that we definitely know is true, right? Because at the beginning, we assumed that D, C, and D, C comma D, belonged to this equivalence class of A and B, right? And so that means that by definition, C and D are both positive integers. The smallest positive integer is 1, right? So again, in order to explain this, we start at the simple thing that we know, and we move up to try and reach the thing that we're trying to demonstrate. So again, so we might start a new paragraph down here, and we'd say something like, since C and D are in the equivalence class of A and B, C and D are both positive integers, and thus D is greater than or equal to 1, which implies minus D is less than or equal to minus 1, which implies L plus B minus D is less than or equal to L plus B minus 1, which implies that K is less than or equal to L plus B minus 1. So we might say something like, therefore, we've shown that what have we shown? That K is between these two bounds, right? Okay, so finally we have concluded goal number 2 on our list was to show that K satisfied these two bounds. And the final thing that we need to conclude is that D is equal to this. So let's just show it. And that follows directly from our construction. So finally, from the fact, I guess we should say, from the fact that C plus 2D is equal to A plus 2B, we have, well, how do we write this? So let's do, so C we could replace with 2K. Let me move this over slightly. So we have 2K plus 2D is equal to 2L plus 2B, which implies that, well, so let's see. Do I want to divide everything by 2? So let's go up and check. What are we trying to show? Yeah, probably we should divide everything through by 2. Got myself confused for half of a second. Got myself, where am I going wrong here? Going wrong in a recorded video, unthinkable. So C is equal to 2K. So, well, let's keep going. So we have K plus D should be equal to L plus B. And this implies that K is equal to L plus B minus D. Yes. Right. So, but we were trying to, what am I doing? We wanted D equal to L plus B minus K. And is that what we had up above? Did I make a typo there? Was it K and 2L plus B over 2? That's where the typo was. There should be a 2 here. There should have been a 2 here the whole time. Okay. That is why we have our rough work and our good work separately. So what we're actually trying to show here, that this is L plus B minus K. That this is L plus B minus K. Yeah, fantastic. Okay, great. So we've shown the thing that we want to show. Fantastic. So because we sort of had 3 separate things, let's review for the reader all the things that we needed to show, right? So we needed to show what? That C is equal to 2k, that D is equal to that in fact D is equal to L plus B minus k, and that k satisfied these bounds, right? We basically needed to show that it's in this set, right? So let's tell the reader. So thus, or hence, maybe haven't used that word yet too much. Hence, C is equal to 2k, where k is an integer between L plus B minus D, and D is equal to L plus B minus K. And so the pair C and D is an element of the set of pairs 2k, and perhaps we should even use separate variables here, just because here I'm using sort of this k. I've sort of chosen a fixed particular k, right? So I might want to write this as a separate variable. So maybe I'll write it as like the set of all 2m L plus B minus m, such that m is an integer where m is between 1 and L plus B. What was the other what was the other condition here? L plus B minus 1. Okay, but that's only half the battle. That's only half the battle. We need to argue in the other direction. So we need to now begin with a pair belonging to this set, and argue that it belongs to the equivalence class of AB. So now we would say something like conversely, suppose that we had a pair. So let's say 2k L plus B minus k being an element of this set of pairs 2m L plus B minus m. Now note again, so it's not a huge deal necessarily, but I am being just extra cautious with my choice of variable names, because over on the right side in the set, m is acting as some sort of arbitrary like dummy variable, whereas on the left side, I'm looking at all of these pairs, and I'm choosing some particular k in that case. So I'm differentiating between m as an arbitrary variable, k is some particular choice, right? So what do we need to do then? So let's think about our goal. Again, separately over here, our goal is to show that this pair, that 2k, L plus B minus k, belongs to the equivalence class of AB, right? So what does that mean? That means I need to show that A plus 2B is equal to 2k plus 2 times L plus B minus k. But what does that mean? That means that 2L plus 2B is equal to, well, if we distribute this out, I mean, this is just this statement, right? Because the plus 2k and minus 2k equal. So this one's a lot easier, right? And I just need to argue that, well, we also need to argue that these are both positive integers, right? So so let's start there. So since k is an integer, and in fact, actually, since K, B, and L, we know, are all integers. 2K and L plus B minus K are integers. We also need to argue that these are positive integers, right? So moreover, and here I'm going to use this inequality here. Since K is less than or equal to 1, that implies that 2 is less than or equal to K. So, 2K. Hence, 2K is a positive integer. And we might need to do a little more work here, right? So I want to show that L plus B minus K. So I want to show that L plus B minus K is greater than or equal to 1. And, well, I do, and I want to work, again, from here. I want to work from my assumption that K is less than or equal to L plus B minus 1, right? So, well, it's not too hard to see to rearrange this equation. I just move the 1 over and I move the K over, right? So, moreover, so we have hence there. We could say, furthermore, by assumption, K is less than L plus B minus 1, and thus 1 is less than or equal to L plus B minus K, meaning L plus B minus K is a positive integer. Nice. Okay. So we have that. We should maybe just add a sentence reviewing to the reader what we just proved, because there's a few extra steps here. So we know that this pair actually belongs to the Cartesian product of the set of positive integers. Fantastic. Okay, so finally, what do we need to do in order to verify that this is in here? We simply need to work out this relation, right? But we already did the rough work. So we just need to work backwards through this computation, right? So finally, and we'll just start with going through this computation backwards, right? So 2L plus 2B, that's definitely equal to itself. 2L plus 2B equal to 2L plus 2B implies that 2L plus 2B is equal to 2K plus 2L plus 2B minus 2K, which is equal to 2K plus 2 times L plus B minus K. And let's see, how far is that from what we wanted to show? Right. So now I will replace the 2L with an A on the left-hand side of the equation, and that will finish satisfying the property, right? And so finally, which implies that A plus 2B is equal to 2K plus 2L plus B minus K. Therefore, the pair 2K, 2L plus B minus K belongs to the equivalence class of A and B. Thus, what have we shown? We've shown that the equivalence class of A and B is exactly equal to the set of all pairs 2M, oh, sorry, there shouldn't be this factor of 2 here. 2M L plus B minus M, such that M is an integer and m is between 1 and L plus B minus 1. So therefore, we might argue that the set on the right is in bijection with integers m such that 1 is between m and L plus B minus 1. Hence, the cardinality of AB is equal to L plus B minus 1, or as I said before, we can rewrite that in terms of A and B, so A plus B minus 2 over 2. Okay, so that concludes the proof for the case of even A, right? So before we go on trying to solve the problem, let me just say that in an entirely similar fashion, again, I'm now going to leave the second part up to you on how to write a rigorous proof. If you ask me really nice in the comments, then perhaps I will do the other part of the proof as well, although I think now you should be equipped to tackle that part of the proof. But the reasoning is entirely similar, right? So just like before, basically the point is that it will come down. We have these conditions. Let's see. I made some notes here just so I wouldn't get myself messed up. So if A is odd. If A is odd, then what? A will be equal to 2L plus 1. And our condition, so if you remember the conditions on our set previously were that we wanted A plus 2B minus X to be even, and we wanted X to be between 0 and A plus 2B. So again, just pulling things out. So this would be 2L plus 1 plus 2B minus X even, which we can see would be exactly the case. So in order for this to be fulfilled, it's true if and only if X itself is odd, right? So these conditions end up, just as before, becoming now the conditions for all 2K plus 1 between 2L plus 1 plus 2B. So that's this second equation here, and K an integer. Right, so it just boils down to this equation. Simplifying things a bit more, it really just comes down to this inequality. So I'll subtract 1 from both sides. So this becomes 2K, 2L plus 2B. And remember that X itself has to be positive, right? So 2K plus 1 definitely has to be positive. And so if we think about what that means here, this can't actually be minus 1. Well, just the fact that this is an integer and strictly greater than minus 1 is equivalent to saying that it's at least 0. And so we have this inequality here. I can multiply both sides by 2, so that becomes this inequality here. Oh, sorry, I did an extra step. And then finally, that reduces to this inequality, K between 0 and L plus B minus 1. So the formula, therefore, in the odd case, would be, well, it's the total number of these numbers, right? So there would be L plus B minus 1, but now we're starting at 0, so the total would actually be L plus B in this case. And remember that A was equal to 2L plus 1, so that's A minus 1 equal to 2L. So A minus 1 over 2 is equal to L, so we could rewrite this as A minus 1 over 2 plus B. Which could be rewritten as A plus 2B minus 1 over 2. So in total, so again, you'd want to go through, do a rigorous proof. Of course, in order to answer the original questions we started with about 13 or 273 elements, you only need one of these cases, I think. But so now we have two cases, right? So the cardinality of the equivalence class of the set will be equal to, so by the above, we had, what was it, A plus 2B minus 2 over 2 when A is even. So let's see. Let's just double check that that is what we had. Yeah, A plus B minus 2 over 2 when A is even. And when A is odd, we have A plus 2B minus 1 over 2 for A odd. And so, well, that might have seemed like a lot of work. Keep in mind, I was trying to go really slow to explain everything as carefully and rigorously as possible. It should be possible to complete this much faster, and certainly much faster than trying to write down, see if you can write down an arbitrary set with 273 elements. Now that we have this very general formula, though, we can solve any of these problems immediately. So we just need to ask ourselves, is it possible? So can we solve A plus 2b minus 2 over 2 equal to 13 in for A even, right? So let's see if we can try and solve this, right? So this would be so A is even, so let's use that information. We know that we can write it as 2L. So 2L plus 2b minus 2 equal to 26. So that would be 2 times L plus B equal to 28 divided by 2. So that would be L plus B equals to 28 divided by 2 would be 14. And so all we need to do is find a pair of integers that sum to 14, where, of course, we need both L and B to be positive integers. And so certainly this is possible, right? So let's just pick, I don't know, the easiest one that comes to mind is if we pick L and B to be 7 and 7, right? So that means that A itself would be 14 and B would be 7. So now we can use this to answer the question above, right? So indeed, by the formulas above, since 14 is equal to 2 times 7, it is even. Hence what? The cardinality of the equivalence class of 14 and 7 is equal to, well, by our formula, it is 14 plus 2 times 7 divided by 2, minus 2 divided by 2. So that is 14 plus 14 minus 2 over 2, which is 28. I mean, I'm just working backwards through everything, which is equal to 26 over 2, which is equal to 13. Okay. What about the case of 273? So let's go ahead and solve that. So again, let's do some rough work first. to figure out. So let's see. Can we solve this? So 2L plus 2B minus 2 over 2. Can we make this equal to 273? So let's go 2L plus 2B minus 2 equals to 600 646. You better check my mental math, because I can tell you guys how to prove stuff. I can tell you how to prove stuff, but sorry, I just gotta turn something off before the very end of this recording. So I got to tell you how to prove stuff, but mental arithmetic always seems to be an issue. Oh gosh, see, and I did something stupid. It is 546. See, I did something stupid. So 546. Yeah, 140. Yeah. Okay. So I'm confident this is correct now. So we have 2 times L plus B is equal to 546. Plus 2 is 548. Can we solve this for positive integers? Yes, certainly, right? So this is going to be L plus B equal to, now we simply need to divide by 2. So this should be 274 in this case, if I'm not mistaken. So again, let's just pick some pair of integers for which this works, right? Again, what's an easy one? I don't know. Choose L equal to 1 and B equal to 273, right? So we could say something like, again, by the established formulas, since 2 equal to 2 times 1 is even, the cardinality of the equivalence class of 2, because remember A is 2 times L, and 273 would be equal to what was our formula? It was 2 plus 2 times 273 minus 2, all divided by 2. So, well, I'll just cancel these 2's. So this would be 1 plus. Did I make a typo right here at the end of the video yet again? Suspenseful music playing. 273 times 2 plus 2 274 L and B 273. What have I done? Another silly. Oh, is A plus 2B? Yeah. So A should be 2. A should be 2. Oh, yes. Sorry. I did make a very silly typo. So we could have these two 2's would cancel out. And then these 2's cancel out. And we're left, of course, with 273. So that is the final answer. End of the video. Okay, great. I don't know how long I've been recording, but far too long. I did not mean for it to take this long. Let me know if you need more help in the comments, and have fun on the final.